Okay, which ones do we have questions on? Trish? 82? Okay. And basically, just to get through as many as possible, I'm going to flip to it on my solutions that I posted and go over it from there. Alright, it says in 82, jet, a 2.75 times 10 to the 6 Newton catapult jet. It's just in scientific notation because it's a big number. Hopefully we all recall scientific notation, how to get out. Times 10 to the 6 means move that decimal place 6 places to the right? It's ready for takeoff. The jet's engine supply a thrust of 6.35 times 10 to the 6 newtons. How much runway will it need to reach its maximum or minimum takeoff speed of 285 kilometers per hour? And that's going to eventually need converted to meters per second as well. All right, but let's think about what they gave us here. That first value they gave us is the one of the jet. The three values gave it, Trish. Well, be careful. Well, yeah, but we call it its weight, right? Because it's in newtons, all right? So if it was in kilograms, it would be its mass. But because it's in newtons, that's already its weight, otherwise known as its force due to gravity, right? Okay, so at some point we'll need its mass, but we'll worry about that in a second. There's a few things on a problem like this we gotta read into that maybe aren't jumping out at us. Number one, a jet that's gonna take off on a runway is gonna start from rest, right? So we gotta assume that and put VI equals 0. This is its takeoff speed, which we do need to convert to meters per second. I did the conversion down here, but the same old one we run into here and there. Kilometers per hour to meters per second. That becomes 79.2 meters per second. And we want to find how long of a runway, right? So that means find D. Now, in this chapter, you're not going to have problems that only use kinematic equations. We told you last week they're going to pop up, but there's got to be something with forces involved. So if you wanted to find D right away, you run into a problem. We only have VI, VF, and we need to find D, right? And there's no kinematic equation that's only going to use just those, right? And one thing I pointed out last week was, wow, that's getting annoying. I'm going to have to put this up a different way. Hold on. I don't know why that keeps coming off. I'm just going to open it straight up on here. I had it up on my Chromebook just in case I had to write on it, but hold on. I don't know why that's doing that. Let's go back up here and just go here. There you go. But anyways, back to what I was saying. There's only one variable that occurs in some of the kinematic equations and in Newton's second law, which is only linked to the new stuff. What one variable? Acceleration, right? So basically, when you start getting VIs, VFs, Ds, Ts as givens, you got to know that red flag that you're going to have to use kinematic equations somewhere, but just not them by themselves, okay? So in the end, I have to find D. In the end, I'll have to use one. But I'm going to have to find A some other way, but through Newton's second law. All right, so that's where I start going to F net equals MA. All right, and it sounds like the only force that's providing the thrust to make it go down the runway is this constant thrust force of 6.35 times 10 to the 6 newtons. Remember, if there is only one force, it is the net force, right? On that axis. This is the axis we care about. This is where the acceleration is going on, right? So we need to use the F net. That's the thrust force it referred to. It is the only force horizontally, so we throw that into Newton's second law and solve for acceleration. We divide over m. We don't directly have m, but they gave us the weight, right? And we know from the weight mass equation, hopefully by now, that we can find one if given the other. So to find the mass, we divide by little g, and that big number there is the mass. So we plug in the thrust force, which is the net force, divided by the mass, and this jet must be accelerating at 22.6 meters per second squared. Now that we have that, we could use it along with this information to use the correct kinematic equation, the one without the t basically, number 3. And we could solve that one for d, and rearranging and making sure we plug in the converted final velocity that's in meters per second, we get just shy 139 meters. So it would need a minimum of that to be able to reach that speed based on the acceleration due to the thrust given there. So that's a pretty typical type of problem. Like, if you're going to use kinematic equations, you're either going to have to find A with Newton's second law and use A in the kinematic equations, or we could shuffle it around. I think we had a tension problem last week where we used the kinematic equations first to find A, and then we used that A in Newton's second law. Either way, that's the only link between like anything new and anything old. So it will always be something like that. Are you okay with that one? Yeah, we did have to convert that number to meters per second. Because the main reason we have to, when we find A, it's in meters per second squared, right? And if that's not in meters per second, then these units won't mesh in here when we run the numbers, okay? So that kind of goes along with what we always said about the kinematic equations. Make sure, you know, or typically want meters for D, meters per second for V's, meters per second squared for A, and T in seconds. All right, other questions? What do we got? A lot of problems. Make sure you're good with all of them. I know it's going to be open book, but still, even with these in front of you, if you have a similar problem that you still didn't really know what was going on, it might be difficult to solve, so use this time to ask. If you guys don't have some, I'll probably pick some. Yeah, Jordan? 23, okay. Okay, this is a good one. This actually brings back, again, kinematic equations for the reasons of free fall. Did I assign you? I did assign you both parts, right? Yeah. Okay. All right. It says a 65 kilogram diver. Since that's in kilograms, that is not the weight. That's its what? Mass. So just make sure we're okay with that, because that's a mistake I see a lot with this stuff. Jumps off a 10-meter tower. Part A, find the diver's velocity when he hits the water. And as a matter of fact, part A I could have assigned you back when we did free fall, because part A solely alone is just the free fall problem. And that means we don't even need its mass. We're going to assume we jumped just from rest, because it doesn't say otherwise. We fell down 10 meters. Remember in free fall problems, when something falls down, if D is given, we got to make it what kind of number? Negative, to tell it it's going that way. And like always with free fall, G is negative 9.8. All those facts don't change that we learned in the past. We want to find how fast it's going when it hits the water. We use equation 3. We do have to solve for VF by taking the square root. And remember, when doing that, your answer could be plus or minus. Since this guy's on his way down, the answer is minus, right? Representing down. So we get about minus 14 meters per second. So that part right there, like I said, I could have assigned you a long time ago, well before forces, because nothing was necessary with forces. But then, yet, the next part is, it says the diver comes to a stop 2 meters below the surface. Find the net force exerted. So we know F net equals ma, right? Since it says find the net force, I don't care what forces make up the net force. I just have to find m times a, right? Now, if I did want to break it down more, there's gravity, right? That's what's pulling you down into the water. And isn't the water pushing back on you as you go through it? But we don't even have to worry about that, because those are forces that make up the net force, but we don't even have to break that down, because it says literally find the net force, right? It just wants it as a total. F net equals ma. So we have the mass as a given, but we don't have the acceleration once we're in water. But this is where our answer to part A comes in. So if you didn't get part A, you couldn't get part B. Our answer to part A was the final velocity when we hit the water, right? But now, for this next part, once we're in the water, that VF of part A becomes my VI of part B. Does that make sense to everybody? Because now I think of it, now I hit the water, I go 2 meters and come to a stop is what it's telling me, right? So going 2 meters, I'm still going to continue to call down as negative, okay? And final velocity, we came to a stop 0. From that information, I could find acceleration. And the acceleration comes out as positive 49 meters per second squared. If we've been calling down negative, which we have been, it should make sense if we remember all our facts about acceleration in the past, that our A came out positive. So remember, if you're moving this way and slowing down, that's what you do when you hit water, right? Moving this way, slowing down, your A better be this way, right? That's all old stuff. Does that make sense? That's corresponds to what's supposed to happen. And all you got to do to find the net force acting on you, again, straight up Newton's second law, that net force equals ma. Take that A and times it by the given mass. This person was 65 kilograms. All you got to do is multiply those two, and we get out 3,185 newtons or something very close to that. You okay on that one? That make sense? Yeah, just make sure. The big thing was realizing this final velocity of the first part becomes the initial of the second part. Find the A. Yeah, question? Which one? Okay, 59. Everybody else good before we move on from this one? Anything on this one? Okay. We got an elevator problem. And this one, I think I told you only do A to D, right? Is that in there? What's that? A, B, C, and D. Right. Alright, but this is a typical elevator problem. It says assume that a scale is in an elevator on Earth. What force would the scale exert on a 53 kilogram person standing on it in the following situations? Okay, so we have constant speed. First of all, let's free body diagram of this situation, like we did for elevator problems before. Normal force up, that's a scale under your feet, right? So the normal force provides the scale reading. So it's pushing up on you, and your weight is always down. So one thing I did right away, because we're going to need it, we were given the mass, I found its weight, which is taking it times 9.8, right? And in our diagram, it shows it pointing downward. And constant speed is when acceleration equals what? 0. So when we use Newton's second law, anytime that's one of two possible equilibrium scenarios, right? At rest or constant speed. In those two cases, if I'm using Newton's second law, the whole right side 0. If MA, if A is 0, 0 times any M is 0. So we do break down the net force into its specific forces for this problem because we want to know what the scale reads, and the scale is going to be the reading of the normal force. Normal force minus weight, the up 1 minus the down 1, equals 0. Therefore, that proves that the normal force should just straight up equal the weight, right? The magnitude, which we already found up here. If you didn't already, that's when you do it. So this person is 519.4 newtons. That's what we refer to as their real weight, right? Because if you're at equilibrium on a scale, that's what you really weigh on Earth. But then we have situations like part B, where it slows at 2 meters per second while moving upward. All right, now this is where we got to be careful. If I'm moving up and slowing down, my A has to be what? Negative, all right? So, and the concept we learn before we even go through any of this math right now is if we have a negative acceleration, does our apparent weight feel heavier or lighter than our real weight? Remember, our real weight's really what I found in part A, right? Because that was at equilibrium. So if I'm undergoing a negative acceleration, will I feel heavier, lighter, or the same? Lighter. So we should expect, knowing that concept, I better get a number lower than this, right? If you wouldn't, then you probably did something wrong mathematically. All right, but we break, still F net is still the normal force minus the weight, still equals MA, but this time MA has to stay around because it's non-zero. So we solve for the normal force reading of the scale, plug in our M, plug in our -2 for A, and take our weight from earlier, since we already found it, we can just plug it right in there. And we do get smaller. This person feels a little over 100 newtons lighter during this negative acceleration period, 413.4 newtons. In part C, I don't have any work because it's the same answer as part B. It says it speeds up at 2 meters per second squared while moving downward. But if you're moving down and speeding up, that's still a negative acceleration, right? So -2. Just remember what I said. Don't get fooled. The biggest mistake is assuming that your acceleration direction is always the way you're moving. That's not the case. You got to think of which way I'm moving. Am I speeding up or slowing down? You got to think about both those things to decide if your A is positive or negative. So since it was -2 again, it would be all the same work. I wouldn't expect you to have to redo all the same work. Just realize it, and it's again 413.4. In part D, it's moving downward at a constant speed. I don't care if it's upward or downward. If it's constant speed, that's equilibrium, right? And that would be the same answer as constant speed moving upward as in part A. Up or down doesn't matter with constant speed. And so it again would be 519.4. E, I didn't want you to do, not because it was too hard. It doesn't tell you anything specific. I didn't want anybody to get confused on E because you can't find an actual numerical value since it doesn't give you an acceleration magnitude. So I didn't want anybody to get messed up thinking you had to there. That's why I skipped part E on that one, so don't worry about that. So that's very similar to one you were assigned when we did elevator one. We all get on that one? Alright, other one. What do we got? Keep asking while we have the time. So I thought I'll put something. I'd rather have you guys say something. Keep thinking about something. I want to go to 62 just because there's a common mistake I see on this one sometimes. It is a tug-of-war problem, but they did something different on this one. Very slight. We had at least 3, maybe 4 tug-of-war problems by now, right? Where basically some person's force this way minus some person's force that way equals MA, right? Find the missing piece. Well, that's still the case. It's how they gave you the information that's easily overlooked. And there's a small conversion. So let's check out 62. It says, after Thanksgiving, Kevin and Gamal use a turkey's wishbone to make a wish. If Kevin pulls on it with a force of 0.17 newtons larger than Gamal in the opposite direction, and the wishbone has a mass of 13 grams, what's the wishbone's initial acceleration when this occurs? Well, think about what it said, though. It's easy to read this too quickly and assume something different. It said if Kevin pulls on it with a force that is 0.17 greater than the other person, right? It doesn't say he's pulling with a force of 0.17 newtons, does it? That's probably the biggest mistake I see on this one, that somebody puts Kevin's force as 0.17 newtons. That is not. That is actually, 0.17 is actually the what force? It's not just Kevin's, it's not just Gamal. What's that? It's the net, right? It's wording in a way, it's not saying jumping up, saying this is a net force, it's making you think. And if you know this concept, that's what the net force is, right? If you have one person pulling this way and one person pulling that way, the net total would be the leftover bigger force, right? Because one's positive, one's negative. So it actually gave you the net, not one or the other, it gave you the net, but that's okay. As long as you realize that, we plug that in on the left side of the formula. And we also have to convert the mass from grams to kilograms. 3 places to the left, that's just a decimal conversion you could use your stair chart for if you need it. And simply plug in 0.17 for the F net, divide over the M, plug in our converted M, and at the moment the net force, when they start pulling and it goes in favor of Kevin because he's obviously pulling harder, it will accelerate at 13.1 meters per second squared. That might sound like a knot for this situation until you really think about it. If you like just grab something from somebody and pulled real quick, that object would accelerate very quickly for a moment, right? Might not accelerate forever, you're probably going to stop pretty quick. But for the moment that happens, a small low mass object accelerates at a fairly high acceleration for the situation. So that's okay. We okay with that one? Just as long as you realize that was the net force given, not a bad problem. All right, anybody think of any they want to see? Yeah, Chris? 92. I didn't give you 92, did I? I don't think. Nobody else has 92 mark, do you? Okay. Sometimes I give that later in the year as a bonus problem, but we didn't talk about anything with like a pulley system like that yet. So don't worry about that one if you tried it, okay? Anything else? I'm going to pick another one. Nobody asked a question yet on like a tension type one. That's what we just did most recently in class. So let's look at 70. All right, it says a grocery sack can withstand a maximum of 230 newtons before it rips. Will a bag holding 15 kilograms of groceries that's lifted from the checkout counter, the acceleration is 7 meters per second squared hold? Remember, yes, usually with tension, it's a rope or a string or something like that, right? But when we first defined tension, we said it could be a rope, string, chain, cable, or anything, any kind of object that could have slack and be pulled tight, right? And isn't a plastic grocery bag like that, right? You could have slack and then be pulled tight, and possibly rip and break, right? So it is a tension problem. It's a upward tension when you pull on the handles of this bag, all right? But remember something big we said when we did an example similar to this, it just had a rope and a bucket. That when it's a will it or won't it break problem, and they give us the max tension, do we actually use the max tension in the solving of it? No, and we stressed that a lot last week. If we were asked to find the max acceleration and we're given the max tension, yes, we would use it in the solving. But if it's a will it or won't it break problem, they're going to give us the max tension. We need to find the actual tension using Newton's second law. Free body diagram, tension's up, weight's down, right? Mass is given, therefore we can find the weight. So if mass is 15 kilograms, we can take it times g at some point. Right here I did it to find the weight. So the weight is 147 newtons. Setting up Newton's second law is the up force minus the down force on the y-axis. That equals ma. A was given as 7 meters per second squared. That's what I yank up on it with, that acceleration. Finding the actual tension based on that acceleration, which means add weight to this side. It's going to be 15 times 7, the mass times the A, plus the 147, the weight. And you get 252 newtons. And now here's where the max tension comes into play. You just compare, right? So this is what it really is caused by that acceleration. It's clearly greater than the max. So this bag's going to break. Anything else? Yeah. Multiplying forces not with using Newton's second law now. Yeah, there could be. The only reason we subtract here is because, again, we got to think, we call one way positive and one way negative, right? And that's true even if it's on this axis we're working on, right? One way's got to be positive, one way's got to be negative. In this case, up positive, down negative, right? That's why we subtract them. Because F-net means total, but total doesn't mean you always add. You only add if they're pointing in the same direction, right? So since this one's pointing negative, that's where we account in this case for weight being negative, so we subtract it off. Okay? But could you have a problem where you add them? Absolutely. We could have a problem, and we probably will in the future when we do more stuff with this next chapter. We could have like two forces pulling on something in that direction. Two people, two different ropes pulling on something or some way. In that case, those people would add together, right? They're going in the same direction. So that's where the free body diagrams come in to visualize it too. So clearly, if they go in the same direction, they get totaled and added that direction, right? But if there's opposite directions, then one direction has to be negative, and that's totaling it up makes it subtract off. Does that answer your question? Any other questions on this or in general? I don't think there are any others. All right, I'll flip around then and see what we got here. Let's just find another one, I guess, then that maybe uses kinematic equations. I know 61 uses kinematic equations. In 61, it says a car of mass 2,300 kilograms slows down at a rate of 3 meters per second squared when approaching a stop sign. What is the magnitude of the net force causing it to slow down? So number one is asking for net force. Asking for net force, we just need to know M and we just need to know A, and we can multiply those, and those give us the net total force already. So we do know M, we don't know A. We do. Oh, actually, I'm sorry, this one's simpler than I thought. We actually don't need kinematic equations. It straight up gives us the acceleration, 3 meters per second squared, right? But we just do have to do this. Was a good one to pick for this reason. Old stuff. If a car's traveling and slowing down, remember what we always said in the past. If they don't define direction, we're always going to assume the way it's going is the what direction. Positive. If something's slowing down at a rate of 3 meters per second squared, that's got to be an acceleration, right? We got to do what to it? So I'm moving positive, and I'm slowing down. My A is actually negative. So just slap a negative on it. Then just take M times A to get the net force. Negative 6,900 newtons. Yeah. 96. Was that the last one? Okay. We may see a variation of this problem in the future when there is friction, but without friction, we'll do it the easiest way possible. Let's see the details here. 3 blocks are connected by massless strings that are pulled along a frictionless surface by horizontal forces as shown. What is the acceleration of each block? The first little note I have on here in the solutions. All these blocks are all connected, right? So could they have different varying accelerations? No, if they did, they wouldn't be connected anymore, would they? So one thing we just have to have mentally an idea is that they all move together, right? They can't have different accelerations unless the ropes broke or something like that, right? Which clearly isn't happening. So because of that, the best way to solve this problem is figuring that the force that's pulling them is 36 newtons. And really, it really doesn't matter if these boxes were stacked on top of each other or connected by these ropes, because it would still feel like you're just pulling a total of the addition of all three. Everybody agree? All right? Because one of them's 2 kilograms, one of them's 4 kilograms, the other one's mass is 6 kilograms. You total that all up, there's 12 kilograms to pull on, right? So the easiest way to view and solve this problem is to call the net force the force that's being pulled on in the picture, the 36 newtons. Now, in the future, if there is friction, it gets more complicated than this. Because there's no friction, there's one force this way that I'm pulling with, and I'm pulling on all the masses combined, right? So I'm going to use the 36 newtons as my net force because that is my only force on the x-axis. I'm going to total up the masses because I'm pulling on all of them, and I'm going to solve for A. If I do that, divide over M, it's 36 over 12, and I have 3 meters per second squared. And again, all of them have to go at that because they're all connected. Does that make sense to everybody? All right. We also will need that. If you couldn't get part A, you wouldn't get to the rest of them later. We then want to know the tensions in what's referred to as tension 1 and tension 2. And here's all you got to think about. The first pull that it gave me, 36 newtons that we call the net force in part A, that force was pulling on all of them because it's out front, right? But tension 2, you can't pull on what's in front of you, right? You can only pull on what's behind you. It's a very similar idea, not the same, but similar to like when we were doing the hanging mass problem. We always said, when there was multiple scales or multiple strings, the string down here only supports what's down here, not what's above it, right? All right. In a similar kind of thinking, strings that are connected to masses like this, the box in front of it is not causing the tension, it's what is pulling behind it. Alright, so for what they called FT2, that tension is pulling on the back two masses, M1 and M2, if you look at the picture, right? So we could use everything's got to keep accelerating at 3 meters per second squared though. So we're going to run Fnet equals MA again, and in this view, Fnet's just going to be the tension 2. Okay, pulling on those. Again, there's no friction to subtract off. So the net force tension 2 is, we're only going to use the mass of the blocks behind it, M1 and M2, which those total up to be 6, because one of them's 2 and one of them's 4. And so when we use Newton's second law to find it, it's just 6 times the acceleration we found in part A, and that's 18 newtons. Does that make sense? And then finally, tension 1 is the one that connects the back two blocks, but the only block that's behind it is mass 1. It's still accelerating at 3 meters per second again, squared. And since it's only pulling on block 1, we take just block 1's mass, which is 2 kilograms, times 3, and we get 6 newtons. Front tension was the most. That was the given one, the 36 newtons, what we called the overall net force on all of them in the first place. And it drops from there because each string pulls on less and less behind it. Yeah, the only reason there's 2 arrows there is because that's when you get into like just the concept of Newton's third law, where for every action there's an equal and opposite reaction. It does cause a two-way thing, but when treating it as just pulling on the back ones, you just got to think it's pulling those back ones forward, right? That was probably, 96 was probably the most different problem we had, but it still had a lot of similarities to the one we did. Anything else? We got a little bit of time. Let's take a look at maybe 79 then. At first glance, this is one of the ones that might look like, whoa, we never did anything like this. But when you think about it, we really did. All right? At least something close enough that we should be able to get this one. A helicopter's taken off. All right? No, we did not do that. But a helicopter's going vertical. What problems did we do about stuff going more vertical? Elevator problems, right? Now, no, there's not a normal force under a helicopter, but there is an upward force, right? And I don't care what you even call it, as long as you identify it. A helicopter could go straight up because there's some kind of lift-up force, right? Or if you just want to call it an upward force, I don't care. There's an upward force, and on the y-axis, there's always weight down, right? So it told us that the mass of this helicopter is 4,500 kilograms. The acceleration was positive 2 meters per second squared. We wanted to figure out what lift force, and they actually called it the lift force. So that's the upward force, all right? And when you do this, doesn't that look like a heck of a lot like either an elevator or a vertical tension problem? We got the upward force minus the downward force is the Fnet, because those are the 2 on that axis, right? Equals MA, and all we got to do is solve for the lift force, which means add over the weight. The weight is the mass times little g, right here, 4,100. And plug in all our other numbers, and we get 53,100 newtons, which is a big number, but this is the force needing to lift the helicopter up. You would expect it to be big, right? So again, it maybe wasn't at first glance looking exactly like the problem we did before, but it really is, other than the name of this force. All right, so there's 2 minutes and I'm on 80. Let's check out at least the idea of 80, even if we don't get to it. Remember, we just recently did a normal force problem last week, where somebody who had a certain weight was handed a box that had a certain weight, right? And remember, as long as you know the concept of the normal force, these kind of problems can be used. The normal force is the force that has to push back, a surface has to push back with. to balance out so you're not moving, right? So every one of you sitting in your chairs right now, whatever your weight plus your chair is, whatever that number is, the floor has to push back on you in order to keep you in equilibrium. In other words, at rest right now, right? Same idea here. We got 3 stacked up blocks. And it wants us to find the normal force between all the surfaces, I believe is how they said it. And it gave you all their mass. Yeah, identify any normal forces between the objects. Alright? So even if we don't get cut off, let's take, we can find all their weights, take each one of those masses times 9.8. This surface right here only has to support what's above it, right? The surface of this block. Just don't count what's below it. Alright? When you're finding normal force, if there's like an object below the surface, that doesn't matter. Okay, it's only what's above it. So the normal force here is just the combined weight of these two. The normal force on the floor is the combined weight on all three, right? The normal force right here is just the weight of the top block. Okay, if you get that concept, that should be a fairly easy problem. Alright, so I think we didn't plan on being able to go over all of them. I think we went over enough of them that should be fine tomorrow. So remember, you guys will be taking it home. You're allowed to have everything out and use as much time as you want. And make sure it's turned in Wednesday by noon. All right.